Hello! So this video is all about Hess's Law. And so Hess is just a chemist and he invented this law. So basically, this is Hess's Law of heat summation. And basically what his law says is that if you add together thermochemical equations, you can add and create a sum of their heats, and that is the total heat. So you add them up and you can get the total sum heat of a reaction. I'm going to get off this ugly brown color. So there's a couple different things that you can do to the equations. The first thing you can do is flip it. And basically what that does is you're just putting the products where the reactants were and the reactants where the products were. It is important to write the state of matter, like the gases here, because sometimes things will have multiple of the same element. When you flip it, you flip the sign. So this one's negative, so I'm making it positive. If it was positive, you would make it negative. And yes, there's also half quotients here, and that is just because these equations are only part of like bigger equations. All right, second thing we can do is either multiply or divide equations. So I'm going to multiply this whole equation by 2. And what you're doing is just multiplying across. So 2 times a half is 2 over 2, which ends up being 1. And then we're going to get 2 for the waters. And if you're going to do something like this, you also need to multiply the enthalpy by 2. Okay, so everything by 2. So this will be 1144 kilojoules per mole. So those are your two options. You can flip an equation or multiply and divide an equation. Okay, that's kind of what we're going to be doing here. So let's look at some of these examples. So this will ask you to calculate what the standard enthalpy is for graphite when it becomes a diamond. So this original equation is our goal. That's what we're going to be trying to get to. When we look at the bottom equations, graphite is on the left and diamonds are on the right. We also can see we have oxygens on the left and the right. So what that does is it looks like this. If you have the same thing on both sides, that means that they can cancel. So anything that's a product and a reactant is basically not part of the equation. So I'm going to cancel out those oxygens, and I'm going to cancel out those carbon dioxides because they're the same, and we're going to add these equations together. What gets left over is carbon, that's a graphite, and carbon, that is a diamond. And so we're adding this together, so we also need to add together their heats. But what you should find is that your final answer will match the given equation. That is how you know that you did it correctly. Okay, so we're also just going to add these two heats together, and it'll give us 1.91 kilojoules per mole. So that is your final answer. Okay, looking at this next one, what I always do is compare the equation to all those given Hess's Law equations at the bottom. So it starts with SO2 on the left here as a reactant, and we have SO2 on the left as a reactant as well. That means that first equation is good. Second one, we have SO3 as a product, and we have SO3 as a product. We don't have to do anything to these equations. The elements are where they should be. And I will say that oxygen will always be tricky in all these different kinds of problems. We can cancel out the sulfurs over here, one on the right, one on the left. But oxygen is going to be a little more tricky. Especially, I know a lot of you guys don't really like fractions that much. So currently we have 3 over 2 oxygens on the left and 1 oxygen on the right. So what that means is 3 over 2 oxygens on the left, and 1 is really 2 over 2, so it's good to think about it like that. So if I cancel out 1 oxygen on both sides, it's essentially the same as subtracting 2 over 2. And what we're going to end up with is 1/2 oxygen on the left and nothing on the right side, which is what we want. So that is good. Honestly, if you just kind of do everything else, the oxygens will just kind of work themselves out. So to finish up this question, I'm just going to add up everything. Anything that doesn't get canceled out is going to drop down to the bottom. So we have the SO2 and then the 1/2 oxygen we talked about on the right side over there. And then as the products, we're going to have just the SO3. Okay. And our change in enthalpy just comes from adding those two things together. And we're going to end up with -99 kilojoules per mole. So that's our final answer there. All right, so those last two were kind of just like example problems. This third one is going to be more realistic. So we need to compare our starting equation to the equations we're given. So we start with 2 carbons here on the left. I'm going to try to color coordinate this a little bit better. And so we find the equation that also has carbon in it. And we can see they're both carbon solids, but the one on the bottom only has 1. That means that this whole equation we need to multiply by 2 so that they match. So on the side here, I'm just going to write multiply this equation by 2. Then we're going to look at the next reactant. So this is going to be H2. And on the left is also H2. So it's a reactant. It is where it should be. That one's good. We don't have to change it. And then last one, we're looking for this C2H2. And we find it as a reactant, but we really want it as a product. That means we're going to flip this first equation. Okay, so I'm going to rewrite these equations on the bottom how they should be. So the first one, I'm just going to flip it so the reactants are becoming the products. So we have to flip it so it matches the original. And when you flip it, you need to change the sign. So this is going to be positive, write this a little more neatly, it's going to be positive 1299 kilojoules. Now the second one, we want to multiply everything by 2. So I'm just going to multiply everything by 2. So that's going to be 2 carbons, 2 oxygens, and that's going to make 2 carbon dioxides. And again, we need to multiply that enthalpy by 2. So negative 393.5 times 2. And that's going to be negative 787 kilojoules. Okay, and the last one, we don't have to change it at all. It's a reactant. That's where we want that H2 to be. And all the other elements, we're just going to hope they cancel out. Really just focus on how the original equation matches the bottom one. I will also say it's also really helpful to line up your arrows so that they're all the same. So all the reactants are near each other and all the products are near each other. All right, so we're going to cancel out things that are the same. So when you look at these, what's the same on the left and on the right side? Because we have to add these all together. So I see this 2 CO2 and this 2 CO2. Those are going to cancel. This water and this water are going to cancel. Okay, and now we do have lots of oxygens everywhere. 2 is really 4 over 2. So we have 4 here, 1 here, 5 on the product side. So those will also cancel. If you're worried about the oxygens, they'll work out. And so we're going to bring down to the bottom everything that we have left over. And we're going to add up that final, all those enthalpies. and we should get the total heat of summation is 226.7 kilojoules. And that whole thing would be your final answer. And what you should see is that your equation you end up with should match the original given equation. And I will say too, you can also do more than one thing to an equation. So like here, I just flipped one of them and multiplied a different one by 2, didn't change the third one. You can flip and multiply by 2 in the same thing. You can also divide. You can use however many numbers that you need. So you can multiply by 4 or 3, or you can divide by 2, 3, etc., etc.